All right, thank you. So we have some time for a discussion session, and we've got some post-it notes, and yeah. So we've gone through all. We had many, right? Like you can see, so we've chosen some of them because we cannot go through all of them. So I'll read out the stuff that was written here, and I'll name the table. Somebody from the table can talk a bit more about it, and we will have some time so that other members in the audience can contribute to the discussion as well. All right. So the first post-it note that I have here is from table 4. Don't know where that is. Um, says when training a foundation model to extract summary stats from huge amounts of raw astro data, how can we minimize uncertainty/error? And so some other points about basically uncertainty quantification, causal intervention, symbolic interpretation, outliers in embedding. Anybody wants to? Where is group 4? Yes. Okay. Let me bring the mic.
Hi, so yeah, these were really great talks, and we were discussing how ML could estimate summary statistics like stellar mass, star formation rate, and morphology from raw data, and wondering how we would quantify uncertainties in these measurements, especially with morphology, since we're not eyeballing these large swaths of Rubin data ourselves. I don't know.
Any opinions on that? Maybe the faculty speakers might have some opinions on this, especially, or others. Yeah, there you go.
So, I mean, the point of uncertainty is an open issue, I think. I think we understand pretty well how to quantify uncertainty when we do now pure supervised, I think. We've been working a little bit on it, and we kind of have good estimations of posterior distributions. Now, galaxy morphology is a special thing because I mean, I'm not sure it's the best example because uncertainties come in many flavors, and the training set is already biased and has its own uncertainty. So it's a very difficult thing in which you want to quantify uncertainties. If you got something like more focused, like stellar masses or something like that, you can more or less estimate uncertainties. Now, if you do from a fully pre-trained model, I'm not sure it's that different, to be honest, because at the end, the thing that complicates the things is that the selection function. That's what Risa was saying at the beginning, that you lose a little bit of control about the selection function. But if you just estimate a posterior distribution from the embeddings, you should be able to capture uncertainty somehow within the limits of any kind of other uncertainty quantification, I think.
Any other thoughts on that? Who wants to? The uncertainty quantification of embeddings. If not, we can move to the next question, which is, are foundation models useful for rare event problems and phenomena? Says, would you design a self-driving car using a foundational model? This is from table 1.
Yeah, we had a sort of spirited discussion around. I think one of the talks had a slide with different percentages and sort of the rarity of what we're looking for. And so, one of the things we were talking about is the fact that obviously, foundation models, despite massive amounts of data input, are still pattern recognizing. And if we're asking them to essentially learn or teach us about rare event phenomena, I think one thing we don't quite understand well statistically yet is their capability in doing so. And so like a couple different examples. One thing that came up at the table that we were talking about is this. There's a nice paper by Adam Kalai, who's now a researcher at OpenAI, that points out that if you want to build a foundation model that has sort of the best predictive performance possible, then hallucination is unavoidable. And kind of the reason is that it needs to be able to fill in, to predict, to complete sentences for everything. And so like the example I gave was, if you ask it to write an obituary for Albert Einstein, it'll do a great job because there's lots of information about Albert Einstein's obituary in the training data. If you ask it to write an obituary for Ramesh Johari, it'll do a terrible job because I'm not dead yet. And there's no training data on an obituary for me, but there's lots of training data on obituaries. So it'll pattern recognize on obituaries and complete that sentence. And so I think like this kind of, where this led to, the self-driving car comment, is that if you contrast sort of what the state of the art is in leveraging foundation models for building things like sequential reasoning, so on, with natural language, that's extremely far ahead. But if you sort of go inside a company like Waymo or Zoox or companies that are trying to build self-driving cars, there's a large part of robotics in high-stakes situations in the real world that still looks very much like classical control with lots of understanding of the systems that we're putting together. And there's just a very big gap between those. And so I think, in the context of the discussion from some of the talks this morning, the question really was, do we, how do we think about bridging the gap from foundation models as large-scale pattern recognizers to foundation models as faithful detectors of very rare event phenomena that we want to understand physically? I don't know if anyone wants to add anything. So, yeah.
Other teams, or no, I think it's super interesting. This gap is certainly there. And so we were chatting about how do we build essentially physics into these foundation models, and I think it's very challenging. I mean, I'm going to be, I guess, purposefully offensive, maybe. I mean, is the end game just a hydra sim, of all these foundation models? It's predictive, but, Any other thoughts on this? Oh, yep.
So I love this discussion because I think it sort of highlights a couple of really interesting differences between, I think, the goals in astronomy and the goals in a lot of more down-to-earth things. And the solution is, if you have a new phenomenon and you're inside an internet company, I remember chatting with people, there's a new phenomenon, they need to be able to recognize this. There will be, you have a labeling team that will label thousands and thousands of samples for something. And if you have an intersection where things are systematically messed up, well, you get more data. And the solution for a lot of problems is you get more data. And if you're in this area, it works great. But for a lot of problems, like for example, the sun only produces 24 hours of data per day. And this is, you can't just like run it forward, and if you had a perfect simulation, you couldn't just, then we'd understand everything. But for all these complex phenomena, you just can't get more data. And I think one of the things I've found for AI, for science type stuff, is often thinking about the difference between I want to discover new things and I just simply want to make something run faster. And in the case of what Mark was talking about at the very beginning, there are a lot of discovery can be reduced to, I just need to get more data. And I have a supervised learning problem where I feel very nice and happy and comfortable. And there are challenges, there's still challenges, but I think trying to tease apart which one is which, is this something where I can just get more data, or is this a problem where, well, I need to find rare things? And ML doesn't have great results right now for the rare things, and it might, but if you can reduce yourself to the problem where you're in supervised learning land, you're a lot happier. And that's where I've been trying to sort of work primarily.
Thoughts on that? Continuing the discussion? Yeah, so the next group want to go over some ideas as well. So group 9, table 9, would it be more robust to use embedding space for statistical studies rather than discovery? So I think it's related to the previous point in a way. Yeah. Oh.
Yeah, it's very clearly related to the previous point. So if we have worries about trusting a foundation model in the fringes of the distribution, specifically for a task where you might want to kind of predict the spectrum of a galaxy for which you have an image, but that spectrum was never observed. So making sort of extrapolatory predictions, which is something that I like in the discovery side of Astro, that is very clearly something people would want to do. But if we have doubts about that, let's flip this around and ask the question, what about bulk properties, which will very easily be learned? And could I do, for instance, in a database of representations, could I do cosmology? Could I do galaxy evolution in the representation space of that? Because these are bulk properties that should represent it, and in the multimodal learning situation should be better learned than in single modalities and potentially with traditional means. That was a question, not a comment.
Thank you. I don't have an answer, but I have some thoughts. I was also at that table, so maybe it's cheating a bit, but I'm wondering about, I'm wondering if that can tap into like a bit of a deeper question of what do we need help the most with regarding the role of AI in and ML techniques in astronomy, because I don't know if we do need that much help with creativity rather than help with dealing with this overwhelming amount of data. Maybe this is enough for now. Yeah, I don't know. Maybe we do need help with new physics as well. I mean, the latter seems a bit more robust to me. Like, yeah, we definitely need to help with navigating these data sets. That's something AI is good at. Yeah. I don't know when we will be able to trust generating new things. I think it will come, but I don't know if this year is the time.
I mean, so that's related to actually group 2. Are you group 2? No.
We are group 9.
Oh, so group 2 says if all our summary statistics are produced, well, no, so not group 2, sorry. See, too many post-it notes. And I only have 2 hands. So, yeah, oh. I lost it. But somehow it basically says, oh, yes, thank you. Group 11, actually. If you have an all-sky generative model, would it be useful at all? ML-based all-sky. Yeah.
Yeah, so this was to maybe reframe the question about whether we would learn things from an all-sky generative model. Even if we didn't learn anything from it, it could still be useful for contextualizing new data, for experimental design, for astrometry as a service, for photometry as a service, for understanding what kinds of data are available in different overlapping ways and what we do or don't know about them and what might be. So just in that regard, for maybe more pedestrian aspects of doing astronomy. And that was, I think we also talked about some of these other things in terms of wondering whether, this is maybe on a different topic, but or a related topic, but connecting to earlier things, whether, I think we were unsure as whether the latent space or the embedding space, like are those even being constructed in the sort of probabilistic ways that we want to actually be able to use them, particularly for lots of low signal to noise data that could map onto very, very different parts of embedding space, and if there are ways that this problem is being attacked right now, where it's all things that are built for infinite signal to noise data are maybe not well matched, and so maybe not always. There's maybe more uses than just learning and discovering new things, although we certainly want to do that. But there's utility just from an empirical point of view in the models as flexible tools.
You don't want creativity in that, right? you want to be consistent, and you don't want hallucinations, and in that sense, right? Yep, have one.
Yeah, just basically commenting on that whole topic as well, especially also on something that you said, Peter. To the question that you were asking, I would say absolutely we do want to have the physics the way we understand it and can describe it to also be a at least a measure for how well a representation space does, in addition to how well it is in describing the data that we observe. Because like the traditional, I would say traditional as in like the density and temperature fields that we use to describe the universe, they are mathematically very efficient. Like we can write down very incredibly simple equations to describe the universe in that coordinate system. But they're pretty bad at describing the data. Like if you really want to map the entire data into that space, you end up solving hydro simulations that need many parts. Like it's computationally a very inefficient space to work in, but it's mathematically or like, and at least for us to reason, we still want to retain some of these properties. And AI excels in getting data efficient representations. And humans excel in getting human understandable representations. And I think we definitely want to have this as a metric of quality for representation spaces.
Maybe response on actually something that, Mark, you showed in one of your slides was the mapping of the simulated data onto representation space spanned by actual observed data was really interesting, because that is effectively, again, you could turn this around and think of the embedding space as a summarizer for doing simulation-based inference. Like, not just as a check whether your simulation is right, but you could, like this idea of could you learn something from your sort of observed galaxy distribution in relation to the physics of that we believe, right? You could turn this around and say, okay, if my simulation matches the same space, the entire distribution of the representation, I probably ran my simulation with the right parameters. And that means that if that had a certain value of the cosmological parameters, maybe I just learned them.
Is the data for that, should that be images as always, or what's the data modality in that case? Anything? Great. You can, yep.
I think one of the things is that first, everyone has a different idea of how to use these embeddings. And so, and depending on the idea we have, we think it's useful or not for what we, and it's difficult to agree on one thing. But I think one common difficulty is trying to, you know what you were saying, trying to explain with human words what's in these embeddings, and we don't have good ways of doing that. And maybe we will never do it. And how we still work with these embeddings, of course, if we say, no, we just want to do predictive tasks or SBI, maybe we don't want to interpret them. You just want to make sure that they are meaningful sometimes, right? If we want to interpret them, then we're a bit stuck. And you know, at the end we end up doing these UMAP things, which, okay. But you know, maybe we need to be more creative on how to find structures in these embedding spaces. I don't know the answer. And we were discussing, I think, yesterday with maybe Francois or something about maybe, you know, we need to ask another AI to look at the embedding spaces and tell us what's in there, because we cannot look beyond 3 dimensions. But maybe some weird agent can do it and start exploring this embedding space and explaining us, you know, well, you know, there's a manifold there that you should look at. It's in n dimensions, but it's there, and then able to explain us what's in. So maybe, I don't know, just maybe science fiction, but you know, why not?
Yeah, no, thank you. Great point. Oh, Sandy.
So just going back to the understanding, can you get any understanding from a large model that produces all the data? I wonder if, like, you know, with such a model, you can do things like intervention. You can conduct these control studies with these models to do some causal discovery. I think there are existing techniques, and people are working hard on some of these questions. I don't know. I think there are probably some causal experts in the audience, and I would love to hear, you know, kind of what the state of art is on understanding kind of models using these kind of intervention, ablation, and what other techniques there are.
Any causal inference experts? But you know, I really do think astrophysics is a really good medium for that, because you know we are in a data-rich space where foundational models are useful, right? But also we have physics models that have been there for decades, that can predict some things, and somewhere in between, if that's what we are interested in, you know, interpretable in human sense, that'd be great as well. And also, I think causal inference and ablation studies are also, I guess, a space that CS people can come to Astro and have a look at, because we have a lot of correlated stuff. You know, we saw scaling relations and so on, right? We have too many scaling relations that we don't understand. I think this is going to be the final comment, and we can go for
I'm
lunch.
going to respond on like the causal inference question.
Oh, great, yes.
This isn't so much about ablation, but I think like, I mean, a couple of related comments. One of them is, it's certainly the case in social science research recently that there's been a number of studies that sort of look at the use of AI and large language models as essentially generators of causal hypotheses, and successfully so. I think one thing that I was talking to a colleague about is that, and I think this is related to the question about using AI to interrogate embeddings. One way that they were describing how to think about that, I don't know if there's research in this way of thinking about it yet, but is essentially that we need enough examples of a reasoning process that allows us to do something like train you know, a machine to recognize manifolds, right? So similarly with causal inference, I think one of the problems is actually that our training data for a successful causal inference is far more limited. And so, you know, where we have kind of a lot of power is in that hypothesis generation phase. But the part of the process that's then carrying that out to consuming evidence, let's say like carrying out observational causal inference entirely algorithmically, there's still you know, a significant gap there in thinking about exactly how we do that in a fully automated way. I think some of the stuff Vasilis talked about yesterday is interesting for that reason, because that sort of idea of automated debiased machine learning is one technique that's very powerful and general purpose applicable for doing something like that. But of course, that's very far away from automated reasoning for causal inference. So. Yeah, no, that's why I knew I didn't. I was not addressing the ablation comment. I think that's a great, yeah, that's a good thing. Good thing.
Great. Thank you. So before we go for lunch, Phil is back again to say something about the...
Okay, all right. Thank you. Sucheta, would you mind standing here, please, and just block everyone's exit route to lunch? Okay. So on the agenda, it says that 12 o'clock is lunchtime. It's not, sorry. We made a change, and we're going to start the unconference right now and have lunch as part of the unconference. So what we'll do is start answering the question for ourselves of how we're going to spend our time this afternoon. We'll try and do it fairly light and easy because you're all exhausted after thinking so hard this morning. But we'll do a bit of organization, then we'll go and get lunch, and then we'll continue in the afternoon. So we're going to do a few things. Let's see. Okay, so first things first. We're going to look at the whiteboard and see what breakout activities have been suggested. If you were one of the people that suggested something on the whiteboard, can you be prepared in about a minute's time to give a 30-second elevator pitch for the session, and we'll see who's interested in joining you. So you know who you are. And Sucheta, maybe when the person stands up to do their pitch, you can run over and give them a mic. Let me go and see what's written on the whiteboard.
And let me just say, if you didn't write something on the whiteboard, there's still time.
Yeah, what we'll do is we'll move this whiteboard over to that side, hopefully, I think, so that you can think about it over lunchtime, sign up, you know, and so on. Okay, we have two things on there. The second one is automated scientist, is it happening? So whoever wrote that, You should be prepared in a minute's time to say something. Francois, very good. Okay, the first one on the list is the one I seeded it with. I thought maybe it might be useful, this is my 30-second elevator pitch, it might be useful to consult the resident Rubin doctors about your big data condition. So if you would like to talk more about the data products coming out in DP1 to help you think about how to do it, we do have some people here who have some understanding, some expertise of the data products. I think we could probably organize ourselves to sit for, say, an hour in a place that you all knew so that you could just drop in to the clinic and ask your questions about data products. Okay, who has a big data affliction and would be interested in coming to that surgery for advice? 1, 2, 3, 4, 5. Okay, so this is an easy one to do. So we'll just find a room and we'll write it on the whiteboard so that you can come and see where to go and at what time. We won't do it all afternoon. Okay, next one, Francois.
All right, so this is not a fully fledged idea, it's more of a discussion topic. And the idea is that we discussed yesterday that a lot more can be done with AI these days. They can code by themselves, they can give you ideas. But the interesting question is, as LSST data starts to come in, what would be the most useful places where we can start to use these tools, and how do we measure their effectiveness? So it could be, for instance, you get some data, you want to build a model for that data. Is it something we can automate? And how can we measure success in that? What kind of benchmark can we build? And over time, what would be the trajectory towards automating as much of the analysis as possible? If you have thoughts on that and you want to brainstorm a little bit, that'd be fun to discuss.
Excellent, good. So that will be some kind of discussion in one of the rooms that we have, and we'll figure that out. So let's see a show of hands. Who would be interested in spending some time with Francois talking about that? 1, 2, 3, 4. Ooh, that's a small copse, if not a forest. Okay, so we'll figure out a room where that discussion can happen. Maybe spend an hour on that, something like that. Okay, and maybe we'll try and time it so that people who want to do both can go to each. Those were the only two suggested. As Risa says, there is always space for more things at the unconference. So when the whiteboard is over here during the lunchtime, you should feel free to pitch some other things, and we can try and help you out, find rooms and so on. Even if it's just a corner of this room, we can figure out how to make that happen.
Is there anyone else who wants to pitch something right now?
Oh, Sucheta.
I was just having an idea related to that. If we can put some concrete example and hack a little bit on that, saying, yeah, for example, yesterday we released a huge catalog of Cosmos Web data with lots of physical information there, photometry and everything. So can we come up with a simple example of an agent asking, we can ask an agent, get this catalog and plot some mass functions or whatever, and how good it is at that. So a toy example with some practical data and start exploring that. Right, I don't know. So I was thinking something.
Good, so I've got discussion led by Francois and then the opportunity to hack with Mark. Excellent, thank you.
Yeah, I would like to talk about some ML-based physics forward models, because this is what I'm working in and I'm still pretty junior, so I would love to talk about this. Because something that has always been on my mind is, well, at some point physics in forward neural networks came up. Then I think people got a bit disappointed because they are a bit hard to train. So what could we now do? Like, has anyone have any experience with pins, or maybe there's something better? But yes, it's a physical model forward model regime. Thank you.
All right, good. Who might be interested in joining Maya for that? All right, good. A small room for that. We can set that up. Who else was? Yes.
I actually just wanted to double down on that idea of talking about, we've discussed all these like interesting foundation models and variational inference and all of this, but yeah, how do we incorporate known physical domain knowledge into our neural networks and not have to rebuild the wheel from the full beginning? Yeah, so more discussion of that.
All right. Was that the same as the forward models or in parallel to the, how would you put it?
They merge, yeah.
Merge them together, double down? Okay, good. Sorry, I've forgotten your name. Can I write it down on the box with you?
Yes. Linnea.
I was going to guess that, thank you. Okay, good. Any other proposals? Yep.
there was a lot of exciting talks and also discussion. I had people about what a galaxy looks like and deblending. I would be curious to have a discussion on undeblending, where you have modeled your image, but then you have done too much deblending. So how do you reconstruct what a galaxy actually looks like? And I think there have been a lot of ideas in the past 2 days, and I think we can really solve this problem. And so if people are curious about to chat more, I'd love to.
All right, that sounds fun. Let me see, who might be interested in joining Viraj for that? Okay, good. So these smaller discussions, we might do them as sort of this table over here with that table over there, make it easy for people, something like that. Okay, any other proposals for unconference discussions? Okay, all right.
You can still write them there, right? I mean, during the lunch period.
Did I what, sorry?
You can still write in them there.
That's true, yes. You can still add down here. And it's nice to, put your initials or something in the right-hand column just so people know that there's interest and so on. Ah, Philip.
Yeah, it's more of a half-baked idea, yet maybe it will flesh out over lunch. But so one thing that has emerged out of the discussion in part is in the forward modeling direction, there's domain knowledge going into modeling everything, and then we have more or less general purpose techniques in then sampling or solving the inverse problem. Whereas when we do the embedding space direction, it's more the other way around, where there's a general purpose idea of finding a good embedding of all the data that we have. And then there's domain knowledge that goes into then answering the physics question that you're interested in. And while they're causally totally different, these two approaches, from an A and B information theory perspective, it feels like just reverting the reasoning. Are there actually some common things that we might already know that we just have to completely reverse engineer our brain and do them? Maybe it's a follow-up on the forward model discussion and the other discussions. I don't know. Maybe it's an own thing. Sorry, very half-baked. Whoever is interested in baking that even further, happy to.
Okay, good. So I think that's something like where to inject the domain knowledge.
Yeah. Thank you for baking.
Okay, and so we've got a note to do that later, maybe, and yeah, same thing. See if you're interested in that, come and vote. Just a quick show of hands. Who thought that might sound fun? Okay, good. So another small copse of people. Okay, so you can see how it works, and the whiteboard will be. There's a little bit more space. We can try and fit one or two more things in. Notice how a number of those were small discussions, the kind of thing you could have around one table. And you might also think, well, while having that discussion, you might think a bit more and think, oh, maybe there's a project here that we could do. And so even while you're in these breakout discussions, it's possible for you to be doing the other thing, which we're doing this afternoon, which is turning ideas into project sketches on napkins. So when you're in one of these discussions, or if you're off with your new friends talking about the things you might do together, make sure you have a napkin and a pen. And now's your chance. So here's just some guidelines for how to do this. It's such a simple thing, I feel silly telling you how to do it. Okay, get together with your prospective collaborators over lunch. Brainstorm a possible project you could do together. Sketch it on a napkin. So today, it's a strange afternoon, right? It's a bit long for an unconference session, as Brant was pointing out earlier, but it's also rather short for a hack session. So this is our sort of intermediate compromise. You can have a hack session where your product, because every hack needs a product, your product is the simplest thing, which is a sketch on a napkin. That's where this is coming from. Okay, so let's give ourselves some other ground rules for napkin making. Okay, goal is to produce a sketch of a new research project captured using the paper napkins and pens provided. Done that. Okay, new project doesn't have to be done by the group that you're talking with. Could be an idea for a project that someone should do. Right? We're brainstorming, putting things out there. Okay, here's a couple of rules I'm going to suggest to you as being a good idea for this exercise. If anyone at any time asks the question, what's the idea here? The group must stop and repitch the idea for the project. Okay? Then another good rule, anyone can join any discussion anytime. And so a good way to get up to speed on that discussion is to ask the question, what's the idea here? And everybody agreed that they would all just stop and tell you. So this is to make it easy to just wander up to a group of people and join in. And they're going to agree to help you by restating the idea for you. So this means that you can also think in terms of more than one napkin. You might do a little bit of discussion with one group and then wander up to another and join in over there. So let's try and get some of that going this afternoon, because I know you're all interested in many different things. Okay, you don't just have to make a napkin. If you have an idea for a project and you think you might go beyond that, hacking, like Mark was saying, with code or with data or something, you can totally do that. That's fine. It's an unconference. You can do what you want. Or as I say, you could stop at the napkin stage and go join another group. That's fine too. Okay, so I showed you this a bit of inspiration on the first day. Napkin might look something like this. So unconferences, hack sessions need products. As I said, the product here is the napkin. You can take it home as a souvenir of this conference, or at least one of you can anyway. I would say if you're ready to commit to actually doing the project together, so becoming proper collaborators and writing a paper together in the end, you should consider signing the napkin to make it a really good souvenir. And then at some point during the afternoon, probably towards the end, a photographer, probably me, will come around and take a photo of each napkin. And if you want, you don't have to do this, but if you want, I could take a picture of you with your napkins as an even nicer souvenir, and it might look good on the website as well. But if you don't want your picture taken, just let the photographer know, that's fine too. Okay, so rule number one, of course, for an unconference is to have fun. So please go and do that, and we'll now go and have some lunch, and you can get started thinking about how you want to spend your time this afternoon.